Dear students, so in previous class we were discussed about the closedness of a set, the convergence of a point, convergence of a sequence, and we also says that every convergent sequence is a Cauchy sequence, but a Cauchy sequence need not be convergence. Every convergent sequence in a metric space is Cauchy. But a Cauchy sequence in a metric space need not be convergent. For consider that X be a metric space, X be a metric space with the usual metric. Here, consider the sequence Xn. Sequence Xn equals sequence 1 by n. With the usual metric d of xy, dxy equals modulus of x minus y. So with respect to this metric d, clearly the sequence xn is a Cauchy sequence. 1 by n, sequence 1 by n is a Cauchy sequence. And we are defined x equals open interval, open closed 0. Clearly, the secant xn means sequence 1 by n which tends to 0 which goes to 0 as n goes to infinity. But the 0 is strictly outside of x. Why? Because x is open closed 0. So a Cauchy sequence need not be convergence in a given metric space. But every convergent sequence is Cauchy, but a Cauchy sequence need not be convergence. Then suppose x be a metric space. If every Cauchy sequence in x converges, suppose this case means every Cauchy sequence in x converges, then that x is said to be a complete metric space. X is said to be a complete metric space. This is an important definition. What is the completeness of a set? How to define the completeness of a set? A set is said to be a metric space is said to be complete. The completeness of a metric space. A metric space is said to be complete only when every Cauchy sequence in that metric space should be convergent. Here we say that a Cauchy sequence need not be convergent, but if in any metric space every Cauchy sequence converges, that metric space is said to be a complete metric space. Agree? So set of reals with the usual metric, is a complete metric space. Clear? Set of reals with the usual metric is a complete metric. What about C? Set of complex plane. Set of complex plane is also a complete metric space. How to approach this one? So let set n be a Cauchy sequence in C. Set n be a Cauchy sequence in C means for all n, m greater than or equals n such that distance between or distance of set n strictly less than epsilon. Agree? Means this is the usual metric d. What is d? Here d equals modulus of x minus y. So that means modulus of set n minus set m. Modulus set n minus set m strictly less than epsilon for all n m greater than or equals particular stage n. Actually, what about set n? Set n means an plus ib. Okay, since set n fall in C, what is set m? Set m equals am plus ibm. Clearly, this an, bn, am, bm, these are real numbers. Agree? So what is set n minus set m? Here set n minus set m is modulus of set n minus set m is modulus of an minus am plus I into bn minus bm. Okay. Now we know that mod an minus am is less than or equals modulus of set n minus set m. Why? When set equals x plus I, why? So mod x less than or equals mod set. It's a real part. So mod an minus am less than or equals mod set n minus set m. But mod set n minus set m strictly less than epsilon. Therefore, an is a Cauchy sequence for all n m greater than or equals n. That means secant an is a Cauchy sequence in where? Cauchy sequence in R. Why? Because an and am are chosen from R. Similarly, modulus of bn minus bm. Mod bn minus bm also less than or equals mod zn minus zn. Why? Because it is the imaginary part of zn minus zn. It is again less than epsilon. That means sequence bn is also Cauchy sequence in R, since bn and bm are chosen from where? R itself. So secant an and secant bn are Cauchy sequence in R, but R is a complete metric space. Hence, this an and bn are converges in R itself. Let an converges to A and bn converges to B in R. This is our assumption. An converges to A and bn converges to B in R. Why? Because an is a Cauchy sequence in R, bn is a Cauchy sequence in R, but an and bn are Cauchy sequence in R since R is complete. Every complete means in R, every Cauchy sequence converges in R itself. So let an converges and bn converges in R, let it be converges to A and B respectively. Now to show that the sequence Zn is chosen from where? C. So it is enough to show that this Zn converges in C. We have to show that C be a, or we tries to prove that C be a complete metric space. So it is enough to show that any Cauchy sequence chosen from C, that it be Zn, is converges in Z. So far, what about modulus of Zn minus Z? Mod Zn minus Z equals modulus of Zn means an plus ibn plus I into an plus ibn minus a plus ib. Z equals a plus I. So which is less than or equals mod an minus a plus mod bn minus b. Okay, but an converges to A, bn converges to b means it goes to 0. So means Zn minus Z converges to 0, means Zn converges to such that Z also is a complex number, means it will fall in C, means every Cauchy sequence in C is converges. Therefore, the given complex plane is also a complete metric space. So this is an important result. Set of reals is a complete metric space with a usual metric D. Similarly, set of complex numbers C is also a complete metric space with respect to the usual metric D itself. Okay. Now let us discuss about an important theorem. That is, let X be a metric space. X be a metric space, and X is complete. X is a complete metric space. Let Y be a subspace of X. Y be a subspace of X, then Y is complete. Y is complete if and only if Y is closed. Y is complete if and only if Y is closed. This is an important result. Means the subspace of a complete metric space is complete only when it is closed. That is the crucial point here. How to prove? First, suppose that Y is complete. Y is complete. That is our necessary argument. First, suppose that Y is complete. Now to show that this Y is closed. So to show Y is closed, first we choose let X fall in X be a limit point of To show Y is closed, we have to show that this X fall in Y itself. X presents in X be a limit point of Y. Our aim is to prove Y. Our aim is Y is complete. So it is enough to show that this X fall in Y. Okay. So X be a limit point of Y. x be a limit point of y means, what is y? Y is a complete geometric space. So x be a limit point of y means for all n following n there exists a natural number n such that S 1 by nx, this is an open ball having or centered at x having radius 1 by n should be positive since n is a natural number. So S 1 by n that intersects always this y minus singleton set x. Why? Because we know that singleton x is always a closed set. Singleton set x is closed. Since singleton set x is closed, then there exists an open sphere centered at x having radius r positive that always intersects this a minus singleton set x. Okay. So with respect to with the light of this argument, then since x be a limit point of y for all n, for there exists a natural number n, then the open ball S 1 by n that intersects y minus x means their intersection is always non-empty. Okay. So let yn presents in S 1 by nx, since it is non-empty, intersects y minus. So let yn fall in S 1 by nx intersect y minus x. A intersection B, S1 by nx intersection y minus x. So that means yn fall in S1 by nx and yn fall in y minus singleton set x. Okay. Yn fall in S1 by nx means what I get? Modulus of yn or distance between or distance of yn and the x strictly less than 1 by n. Okay. Yn fall in y minus x means yn strictly differs from x. Yn fall in y minus singleton set x means yn strictly differs from x. Since yn differs from x and dy nx less than 1 by n and this 1 by n tends to 0 as n tends to infinity, so that means this yn tends to x. But yn differs from x, modulus of yn minus x strictly less than 1 by n. This 1 by n tends to 0 as n tends to infinity, so yn tends to x. 1 by n tends to 0 as n goes to infinity. Okay, so that means sequence yn is sequence yn converges. Sequence yn converges. Okay, so sequence yn converges, but every convergent sequence is Cauchy. Therefore, secant yn is a Cauchy sequence in y. So that means sequence yn is Cauchy. Sequence yn is Cauchy. Okay, but what is y? Yn converges. We know that every convergent sequence is Cauchy. So yn is yn is Cauchy in y. But what is y? Y is complete. Means y is complete. So that yn converges in where sequence yn converges in y. Sequence yn converges in y. Sequence yn converges in y means sequence yn converges to where? X. So that x fall in y. But what is x? X is a limit point of y. Since x is arbitrary, y consists of all of its limit points, then that means y is closed. So this is our necessary argument. So when x is a complete geometric space, y is a subspace of x, then y is complete only when y is closed. So first part is finished. Agree? So come to the reverse inversion. Now, next suppose that reversely suppose that y is closed. You have to prove y is complete. So, let us sequence yn is a sequence yn be a Cauchy sequence in be Cauchy, sequence yn is Cauchy in y. So that means, what is y? Y be a subspace of x. So that means sequence yn is sequence yn be a Cauchy sequence, in X itself. But what is X? X is complete. Since X is complete, surely this sequence yn converges in X. Why? Because X is complete. Since X is complete, sequence yn converges in X. So let sequence yn converges in X, let yn converges to X, small x. That means let X equals limit to y. Let X equals limit to y. That means yn converges to X in X. Okay. Then X is a, that means X equals limit to yn. So this X is a limit point of y. Why? Because yn fall in y. So X is a limit point of y because y is closed. Okay. Since y is closed, X is a, so y consists of all of its limit points. So X is a limit point of y. X is a limit point of y means y is closed. Then X fall in where? X fall in y. Therefore, X fall in y means every Cauchy sequence in y is converges. Hence, it is complete. So the reverse equation is also finished. Okay. So this is an important result. Clear? Yes. Now, let us discuss an important theorem, which is Cantor's intersection theorem. Cantor's intersection theorem. So the theorem we will discuss in next class. Thank you.